What if I told you that a three-man garage operation running out of a converted barn in Ohio discovered something that McLaren, Ferrari, and Mercedes all missed? Not through million-dollar wind tunnels or supercomputers, but with a borrowed dynamometer, some welding equipment, and an approach so unconventional that professional race engineers literally laughed when they saw it. This is the story of how conventional wisdom in racing got turned on its head by people who couldn't afford to think conventionally. Owner and picture this. It's March 2019 at Sebring International Raceway. The who's who of endurance racing are there. Factory teams with semi-trucks full of spare parts, armies of engineers staring at telemetry screens, drivers who've won Le Mans. And then there's Midwest Motorsports Dynamics, rolling up in a converted RV, towing a trailer they bought used off Craigslist. Their entire race budget for the season? Less than what Porsche spent on catering that weekend. The Paddock talk started immediately. Veterans pointed and snickered at their setup. The car, a modified Ligier JS P320 they'd bought as a write-off from a crash, looked wrong to trained eyes. The rake angle was all off. The spring rates made no sense. The damper settings violated everything taught in vehicle dynamics textbooks. One Rebellion racing engineer was overheard saying it looked like someone had set up the car using a smartphone app. He wasn't entirely wrong. And what nobody knew was that this wasn't ignorance. It was revolution. You see, Mark Dennison, Jim Catalano, and Terry Washington weren't stupid. They were broke. And being broke in motorsport forces you to think differently. Dennison had spent 15 years as a suspension tech at various IMSA teams before getting laid off when his team lost sponsorship. Catalano was a mechanical engineer who'd been designing agricultural equipment until the company moved operations to Mexico. Washington? He ran a small machine shop that mostly made parts for local factories. Together, they had about $200,000, a barn, and an idea that everyone said was insane. Here's where it gets interesting. Iron traditional racing setup philosophy, the kind taught at every racing school and used by every professional team, is built on decades of accumulated wisdom. You start with spring rates calculated from corner weights and expected G-forces. You set your ride height based on aerodynamic efficiency. You adjust dampers to control weight transfer rates. Anti-roll bars balance the car through corners. Toe and camber follow established curves based on tire data. It's systematic. It's proven. It works. But Dennison had noticed something during his years in the paddock. Every team was converging on essentially the same setups. Sure, there were minor variations, but everyone was working from the same playbook. The same simulation software, the same tire models, the same fundamental assumptions about what makes a car fast. And here's the thing, when everyone thinks the same way, everyone hits the same walls. The conventional approach assumes you're optimizing individual parameters to theoretical ideals. Spring rates that give you the right ride frequency. Dampers that control oscillation within specific bounds. Roll stiffness distributed to match the car's weight distribution. Alignment that maximizes tire contact patch through the corner. It's all very logical, very scientific, very expensive to get right. But what if the entire approach was asking the wrong question? The birth of what would later be called the Dennison method started in 2018, 6 months after Mark lost his job. He was in his garage, staring at suspension data he'd secretly copied onto thumb drives over the years. Not proprietary stuff, just general setup sheets and telemetry from various cars he'd worked on. Something bothered him. Cars with theoretically inferior setups would occasionally post competitive lap times. Not often, but enough to notice. These outliers were always dismissed as flukes, driver having a good day, track conditions suiting that particular setup, statistical noise. But Dennison started plotting these outliers, looking for patterns everyone else ignored, and he found something fascinating. The fast outlier setups had no consistency in their individual parameters. Spring rates all over the map. Ride heights that varied wildly. Damper settings that seemed random. But they had one thing in common that nobody measured because nobody thought to measure it. The relationship between front and rear natural frequencies under combined loading conditions. And let me explain this in plain terms. Every suspension has a natural frequency, the rate at which it wants to oscillate, like a tuning fork. Traditional setup philosophy says you want the front and rear frequencies within a certain range of each other, typically measured in static conditions. But Dennison realized that under real driving conditions, braking, accelerating, cornering, often all at once, these frequencies shift dramatically, and more importantly, they interact. And then think of it like this. You know how noise-canceling headphones work? They produce a sound wave that's exactly opposite to ambient noise, canceling it out. Dennison discovered that certain Era-Rungen suspension setups created a similar phenomenon. The front and rear suspension oscillations would interfere with each other destructively, canceling out unwanted motions. The car would become incredibly stable and predictable, even though every individual measurement looked incorrect. The problem? You couldn't calculate this with traditional methods. The interactions were too complex, too dependent on dynamic conditions. Simulation software didn't model it because nobody knew to look for it. The only way to find these magic combinations was through exhaustive testing that would cost millions of dollars. Unless you got creative, this is where Catalano came in. Remember, he'd been designing agricultural equipment, combines and tractors that had to work on wildly varying terrain. The agriculture industry had developed some interesting approaches to suspension dynamics that motorsport had never considered. Why? Because racing happens on relatively smooth, predictable surfaces. Farm equipment has to function in chaos. Onoses and Catalano had worked on self-leveling systems that used predictive algorithms to adjust suspension in real time based on terrain scanning. But more relevant to our story, he'd developed methods for testing suspension performance using accelerometers and basic data logging that cost a few $100s instead of hundreds of thousands. Agricultural engineers had to be cheap. Their customers were farmers, not Formula One teams. Together, Dennison and Catalano started developing their theory. But theory doesn't win races. They needed a car. They needed to prove this could work. That's when Washington joined the picture. His machine shop was struggling, and he was looking for something new. He had fabrication skills, and more importantly, he had a dyno, a 20-year-old engine dynamometer he'd bought from a closing speed shop. It wasn't much, but it was something. In October 2018, they pooled their resources and bought the wrecked Ligier. The previous owner, a gentleman driver who'd stuffed it into the wall at Road Atlanta, practically gave it away. The tub was straight, but everything else needed work. Perfect for 3 guys with more time than money. Now here's where their approach diverged completely from everyone else's. Instead of trying to fix the car to proper specifications, they decided to use it as a test bed for their frequency interaction theory. They built what Catalano called a H-resonance map, basically testing thousands of setup combinations to find the ones where the destructive interference pattern emerged. The testing process was insane. They'd bolt on different spring rates, adjust ride heights, change damper settings, and run the car on the dyno with Washington's shop floor covered in industrial rollers they'd salvaged from a closed factory. The car never moved, but the suspension cycled through loads that simulated cornering, braking, and acceleration. Accelerometers taped everywhere recorded the results. And then in 3 months, 12-hour days, 7 days a week, they tested over 4,000 different configurations. Their neighbors thought they were crazy, hearing the engine screaming in the barn at all hours. But patterns started emerging. Certain combinations of seemingly wrong settings produced remarkably stable platforms. The car would hit a pothole that should have upset it, and nothing happened. The oscillation just disappeared. And again, by February 2019, they'd identified 12 setup configurations that showed promise. But dyno testing only tells you so much. They needed track time. Private test days cost money they didn't have, so they entered the car in NASA endurance races, small-time events where they could run long stints and gather data. Nobody paid attention to them, just another privateer team making up the numbers. The data was revealing something extraordinary. Their theoretical lap times should have been 3 to 4 seconds off the pace based on their spring rates and ride heights. Instead, they were within a second of much better funded teams. And here's the crucial part. Their lap times were incredibly consistent. While other cars would vary by 2 or 3 seconds, depending on fuel load and tire wear, the Midwest Motorsports car varied by half a second at most. Nenschten inconsistency doesn't sound sexy, but in endurance racing, it's everything. A car that's 1 second slower but maintains that pace for 4 hours will beat a car that's faster but degrades. Dennison's setup wasn't producing the fastest single lap, but it was producing the fastest average lap over a stint. The destructive interference pattern was preventing the normal degradation of handling as conditions changed. And none. So, they decided to go big. They entered the IMSA Michelin Pilot Challenge race at Sebring as a one-off. It was supposed to be their proof of concept. Show up, run consistently, gather more data, maybe attract some investors who could fund proper development. Then the scrutineers who inspected their car before the race were confused. Everything was legal, but nothing made sense. The front springs were 200 pounds per inch stiffer than anyone else ran. The rear ride height was 15 millimeters higher than optimal. The front anti-roll bar was disconnected entirely. One official pulled Dennison aside and asked if they needed help with setup. Dennison just smiled and said they were good, and on practice sessions made them a laughingstock. Photography enthusiasts were taking pictures of the car because it looked so visually wrong going through corners. The nose was too high, the rear squatted too much under acceleration. It rolled like a boat in transitions. A data engineer from one of the Porsche teams pulled up their telemetry on the timing screens and started using it in a presentation to his drivers about what not to do. But Dennison's team wasn't worried. They knew what others didn't. The car looked wrong because human eyes expect to see certain attitudes that indicate performance. We associate flat, stable platforms with speed. The Midwest car was doing something different. It was allowing specific frequencies of movement while completely canceling others. It looked loose, but was actually more controlled than anything else on track. End qualifying was where things started to get weird. In a field of 38 cars, Midwest Motorsports qualified 15th. Not amazing, but for a 3-man team running a rebuilt wreck, it raised eyebrows. The Porsche engineer who'd mocked them earlier pulled their speed trap data. Down the straight they were slow. The draggy setup cost them 5 miles per hour, but their minimum corner speeds were inexplicably high. Through the carousel, one of Sebring's slowest corners, they were carrying 4 miles per hour more than cars with twice the horsepower. Warren race day, 4 hours of racing on one of the roughest tracks in North America. Sebring is notorious for its bumps, concrete patches, and transitions that upset cars. It's where good setups go to die. The conventional wisdom was to run soft springs to absorb the bumps and deal with the handling degradation as the race wore on. Then at the start was chaos, as always. 3 cars made contact in turn 1. Dennison, driving the opening stint, kept it clean and settled into a rhythm. Lap after lap, the times stayed consistent. 158.2, 158.5, 158.1, 158.3. While cars ahead were varying by seconds as they dealt with traffic and degrading grip, the Midwest car just kept clicking off the same times. And in and an hour in, something remarkable was happening. They were still running 15th, but the gap to the leader hadn't grown. In fact, it had shrunk. Not because they were getting faster, but because everyone else was getting slower. Tire degradation, fuel load changes, brake fade, all the normal things that slow cars down over a stint weren't affecting them equally. And then came the first round of pit stops. Professional teams with practice crews could do a driver change and 4 tires in under a minute. Midwest Motorsports? They had Washington doing tires on one side, while Catalano did the other side, and Dennison jumped out. 2 minutes and 15 seconds. They lost 3 positions. But here's where the magic really started to show. Catalano took over driving, and the lap times didn't change. New driver, worn engine, hotter track temperature, and the car was still doing 158s. The BMW ahead of them had fresh tires and a professional driver, but was only marginally faster. And as those tires wore off their peak, the BMW's time started dropping while Catalano kept hammering out the same pace. And 2 hours in, they were back to 12th. Teams ahead were starting to have problems. A Porsche had a brake issue. A McLaren spun in turn 17. An Aston Martin had a suspension failure, specifically a damper that couldn't handle Sebring's brutality. The Midwest car just kept going. No drama, no degradation, just relentless, metronomic pace. The turning point came at hour 3. A full-course caution for a crashed Mercedes bunched up the field. Everyone pitted. Fresh tires, full fuel, drivers swapped. But when racing resumed, something had changed in the car ahead of them. The professional teams had all made setup adjustments during the stop. Tire pressures, anti-roll bar adjustments, whatever they could touch in the time allowed. They were chasing the changing track conditions. In Midwest, Motorsports changed nothing. They couldn't. Their setup only worked at exactly the settings they'd discovered through thousands of hours of testing. Any adjustment would break the harmonic balance that made it all work. So Washington climbed in for the final stint with the car exactly as it had started the race. The track was different now, rubbered in, hotter. The bumps had gotten worse as the concrete expanded in the Florida sun. Cars that had been fast in the morning were struggling. But Washington's times were still 158s. Competitors who'd been lapping 2 seconds faster in qualifying were now lapping slower than the ugly, wrong-looking Ligier. Wednesday, with 40 minutes to go, they were in 8th place. Teams were starting to notice. Radio chatter increased. Spotters were warning their drivers about the mysteriously fast privateer. The TV commentators finally mentioned them, though they got the team name wrong, calling them Cause Midwest Motors den Puanden Drama. The 5th place Audi had a tire failure. 7th place McLaren had an electrical issue. Suddenly, with 20 minutes remaining, Midwest Motorsports was running 6th in their first real race, with a rebuilt wreck, against factory-supported teams, and the engineers in those teams were scrambling, pulling telemetry, trying to understand what was happening. The data made no sense. The Midwest car's damper histograms showed massive suspension travel that should have resulted in bottoming out and instability. But the G-force traces showed incredibly smooth, consistent cornering. It was like the suspension was moving, but the chassis wasn't. 15 minutes to go, 5th place. The Mercedes ahead was struggling, its driver reporting that the car had become unpredictable. Behind them, a charging Porsche was closing fast, the driver pushing hard for a podium finish. Washington, a 53-year-old machinist who'd never raced professionally, was about to be in a sandwich between 2 funded teams with proven drivers. The Porsche caught them with 10 minutes left. Into turn 1, the Porsche dove inside. Washington didn't fight it. But through the carousel, that same corner where they'd been inexplicably fast all day, Washington got a run on the exit. The setup that looked all wrong allowed him to get on the power earlier, accelerating while the Porsche was still balancing the car. And down the back straight, they were side by side. The Porsche had more power, but Washington had momentum. Into turn 10, the Porsche again took the optimal line. Washington took a wider entry, carrying more speed, using the setup stability to run a line nobody else could make work. On the exit, he was ahead. N5 laps to go. The Porsche driver was clearly faster in Sector 1. Washington was faster in Sector 3. Lap after lap, they traded positions. The TV commentators were going crazy. This nobody team was racing wheel to wheel with a factory Porsche. The David versus Goliath narrative wrote itself. None, but here's what the commentators didn't know. Washington wasn't really racing the Porsche. He was just driving his laps. The same 158s he'd been doing all stint. The setup was so consistent, so predictable, that he could place the car exactly where he wanted it, lap after lap. The Porsche driver was the one doing all the work, fighting his degrading tires, wrestling an increasingly unbalanced car. Nor the last lap. Washington was ahead by half a second starting the lap. The Porsche made one last desperate lunge in turn 7, but Washington's corner exit was again superior. Through the S's, where bumps upset everyone, the Midwest car floated through like it was on rails. Across the line, 5th place. Their celebration was subdued. They knew they'd just proved something significant. The Paddock reaction was immediate and dramatic. Engineers from major teams descended on their pit area, asking questions, taking photos, trying to understand what they'd just witnessed. The data acquisition specialists were particularly intrigued. How had they achieved such consistency with such an apparently wrong setup? Annan Dennison was diplomatic, but vague in his answers. He talked about holistic balances and how dynamic optimization, without revealing the frequency interaction principle. Catalano, ever the engineer, couldn't help but drop hints about agricultural suspension theory that went completely over everyone's heads. Washington just smiled and said they got lucky. But the professional teams knew this wasn't luck. That night, CFD simulations were run. Suspension kinematics were analyzed. Millions of dollars of engineering resources were thrown at understanding how 3 guys in a barn had embarrassed them. The Porsche engineer who'd mocked them earlier publicly apologized, admitting he'd learned something valuable about assumptions. And what happened next changed everything. Within a week, Dennison received calls from 3 major teams offering him consulting contracts. Catalano was approached by a suspension manufacturer wanting to commercialize their method. Washington got orders for custom parts from teams wanting to experiment with similar setups. They turned them all down. Instead, they published their findings, not in a racing magazine or engineering journal, but on a free website, complete with data, methodology, and the theory behind frequency interaction suspension tuning. They open-sourced something that could have made them millionaires. Why? Dennison explained it simply, and racing had become too expensive, too exclusive. The same teams with the biggest budgets always won, because they could afford to optimize traditional setups to the nth degree. We wanted to level the playing field, show that innovation doesn't require millions of dollars, just different thinking. The impact was immediate and controversial. Traditional suspension companies disputed the findings. Several prominent race engineers published rebuttals. But privateer teams around the world started experimenting, and more importantly, they started succeeding. Within 6 months, variations of the Dennison method were being used in everything from karting to GT racing. The major teams eventually adapted, of course. They had to. Mercedes developed a computer model that could predict frequency interactions, though it required a supercomputer to run. Ferrari created active suspension systems that could adjust harmonics in real time. Red Bull hired Catalano as a consultant, though he insisted on working remotely from his barn in Ohio, but the real revolution wasn't technical. It was philosophical. The Midwest Motorsports story proved that racing's accumulated wisdom could be wrong, that sometimes starting from scratch with no preconceptions could lead to breakthrough innovations. It democratized speed in a way that hadn't happened since Colin Chapman started building Lotuses in a garage. The story has a bittersweet epilogue. Midwest Motorsports only raced 3 more times. They won once at Mid-Ohio, beating a full field of professional teams in the rain, where their setup's stability advantage was even more pronounced. But success brought attention they didn't want. Sponsors called. Investors showed up. The simple joy of 3 friends solving problems in a barn was being replaced by business meetings and contracts. And so they stopped, sold the car to a museum. Dennison went back to working as an independent suspension consultant, but only for underfunded teams. Catalano returned to engineering, designing suspension systems for emergency vehicles using racing principles. Washington still runs his machine shop, though now half his business comes from racing teams wanting custom parts. Nonetheless, they campaigned SITs in the International Motor Racing Research Center in Watkins Glen. There's a plaque that lists its specifications. Spring rates, front 800 lbs in, rear 450 lbs in, ride height, front 65 meter, rear 80 meters. Anti-roll bars, front disconnected, rear 25 meters, numbers that still make engineers shake their heads. But there's a second plaque that matters more. It contains a quote from Dennison. "We didn't prove that conventional wisdom was wrong. We proved that unconventional wisdom could be right." In racing, like in life, the biggest barrier to innovation isn't technology or money. It's the assumption that the way things have always been done is the way they must be done. The frequency interaction principle is now taught in engineering schools. It's called the Dennison-Catalano effect in textbooks. Major racing series have had to adjust their regulations because the setup windows that once seemed reasonable now exclude potentially faster configurations. The playing field hasn't been completely leveled, but it's a lot flatter than it was. The story of Midwest Motorsports dynamics isn't really about suspension frequencies or harmonic interactions. It's about what happens when people who can't afford to think conventionally are forced to think creatively. It's about questioning fundamental assumptions. It's about the danger of expertise becoming dogma. And then today, when young engineers enter motorsport, they're taught both methods, the traditional optimization approach and the frequency interaction method. But more importantly, they're taught the Midwest Motorsports lesson, that sometimes the best solution is the one nobody's looking for because everyone knows it's wrong. The racing establishment had spent decades refining their approach, optimizing every parameter, simulating every scenario. They had convergent evolution, everyone arriving at the same solutions because they were using the same methods. What they needed was divergent evolution. Someone to approach the problem from an entirely different angle, that someone turned out to be 3 guys who couldn't afford the conventional approach. In the end, the technical innovation was impressive, but not unprecedented. Destructive interference had been used in other fields for decades. What was unprecedented was applying it to racing suspension, and more importantly, having the courage to stick with something that looked wrong to everyone else. Engine racing will always be about going fast. But Midwest Motorsports reminded everyone that there's more than one way to define fast. Sometimes it's not about the highest peak speed or the lowest individual lap time. Sometimes it's about consistency, predictability, and maintaining performance when others can't. Sometimes the tortoise beats the hare not by becoming a hare, but by being a better tortoise. The next time you watch a race and see a car that looks wrong, riding too high, rolling too much, doing things that shouldn't work, take a second look. It might just be someone who can't afford conventional wisdom finding a faster way to the finish line. Because if 3 guys in a barn can outsmart Formula One teams, what other impossible things are possible? What unconventional solution Have you discovered that experts said wouldn't work? Drop a comment below. And if you enjoyed this deep dive into how questioning everything can lead to breakthrough innovation, hit that subscribe button for more stories of engineering rebels who changed the game.